Ngalakin Khadijan Nyunga Boja.
Video 6. We'll start looking at the idea of normalization, which is a fancy word for saying, how do we arrange our data between different tables so that we have a minimum of redundancy, but not too much overhead in collecting all the data back together again. So we'll look at an example to start with. Imagine we're just storing some geographical data and we're not thinking too much about it, and we're just going to store everything that we want in a spreadsheet. So, for example, this spreadsheet is based around cities. So for each city, so here's London. So London is this city here. We're going to store the country in which it lies, that's England, the continent in which it lies, that's Europe, and the capital city of the country, that's London itself, and the population of the city. This is data from a very old MySQL sample database, so you can ignore the actual values for population and things like that. This is just an illustration for database purposes. Okay, this is quite a bad design for storing data. And we need to work out why it's a bad design, what the problems are with it, and how these problems can be overcome. So let's sort of just think about that structure. Well, it's just a single table. Each row stores all of the data for one city. So there's one city per row, and then each column stores the values of some attribute. Okay, there's nothing wrong so far, but when we look more deeply, we'll see that this design has a couple of problems. First of those problems is redundancy. Data is stored in several different places. The same data is stored in several different places. And fragility, which means that you can easily break this when you don't really have to. This data structure is difficult to maintain in a state of high data integrity. Okay, here are the sort of traditional three ways in which a problem can be caused by a database whose structure is not very suitable. These things are called anomalies. So anomaly just means some error or inconsistency. And these three anomalies arise in the course of doing three standard database operations. The first of those is an insertion anomaly. Okay, inserting a row may require you to know irrelevant information, or irrelevant information to the bit of information that you're trying to include into the database. If you want to include a new city into your database, then the current structure requires us to fill in all of those values. So the continent, the country it's in, the capital of that country, the new city, and then the population of that new city. Well, we shouldn't need to enter data about continents and countries when all we're doing is adding a new city to our database. So the fact that the continent that the country lies in is whatever it is something that the database should already know. We shouldn't have to retype in stuff that's already contained in the database. So that's called an insertion anomaly. A deletion anomaly is sort of the opposite. When you delete a bit of information, you might accidentally delete some additional information that you didn't really want to delete. So if you delete the last city from a particular country, then you no longer know what the capital of that country is. So that may arise when you're sort of using the database and you want to sort of maybe update some values So you delete some things and put some new things in, but when you're doing the deletion, you accidentally delete too much. Third one is an update anomaly, and that occurs when you want to update something, but you end up having to update that same thing in many different places. Countries change the name of their capital all the time, and ideally, if a country changes its capital from, say, Peking to Beijing, then you should just make one alteration, changing Peking to Beijing, and that should be that. But with the database design that we've just illustrated, every city in China will have that, old information about the capital being Peking, and you'd have to change all of them. Okay, so these are ways in which the database can end up in an inconsistent state because we have designed the database badly. The real problem is that each row is trying to keep track of too much. So each row contains some information about the cities, so the city and the population and so on, and also some information about countries, the capital of the country and the continent in which the country lies, and so on. And these two concepts have very different granularity. So that means level of detail. So there are lots and lots of cities, and for each of those cities, we keep storing the information that England lies in Europe, that China lies in Asia. Those sort of things are stored over and over again in that table, even though we really need only one copy of the piece of information that says that China lies in Asia, and that will then apply to all of the many, many cities in China. So the solution then is to split the information into more than one table so that each table keeps track of the data related to just one logical concept. So in this case, we'll want to have a table for cities, for example, and that will contain the city information, and then a separate table for countries, and that will contain sort of the country level information. Okay, this process is called the process of deciding how to split your data between different tables is called normalization, and we'll cover that later. Normalization is sort of common sense at the lowest level and a very complicated mathematical discipline at the higher levels. We're just going to focus more on the sorts of types of normalization that you would intuitively do if you were looking out for the right sorts of things. Okay, so let's have separate tables. Okay, so for the country data then, we're just going to keep track of the continent that contains the country itself, and the capital of that country. So again, this is really, this table is really focused on the country itself. It contains one bit of information about something like bigger than itself, the continent, and another bit of information about something smaller than itself, like a city contained in there. So Thailand has capital Bangkok and lies in Asia. So that's what that row means. Now we've saved here because now we're never going to repeat that information about Thailand and Bangkok and Asia, because for all of the other Thai cities, or for all of the Thai cities, the information is going to be stored somewhere else. In fact, it's going to be stored over here in this city table. So let me give these names. I'll just call this country, and I'll call this city, and they're the names of the tables. Okay, so the city table now contains, well, London has this population, Manchester has this population, Paris has this population, and so on. So we've reduced redundancy. But unfortunately, we've reduced redundancy too much, because we've managed to completely lose track of, like, the country that London lies in. Okay, so somehow we need to connect back these tables in such a way that we can answer questions like, in which continent does the city of Aziza lie? And I've got no idea whether that Aziza is pronounced like that or not. In fact, I'm sure it's not, as we'll see later. Okay, the point is, Aziza information is entirely within the city table, and the only thing we can find out from the city table is population, and so we're sort of missing a link here. Okay, so what we have to do to make this all work is we have to connect the tables to each other, but connect them in an efficient fashion. So the way we're going to do that is we're going to add a column to the city table, and that column is going to contain the country that contains that city, and that country is going to refer to one of the countries in the country table. So in this situation, an attribute of one table that refers to an attribute of another table is called a foreign key. Now, don't worry about that too much yet, but it will become important later. So this is going to be a foreign key. The point of that is that if we were to say, okay, what continent contains Bangkok, then we could look up Bangkok in this table and discover that its country is Thailand. Thailand is then a foreign key to the country table. So we could now go and look up Thailand in the country table. And once we've found that, then we can read off the information that we need. Okay, so a foreign key then is when a single attribute in one table refers to a row of another table. Okay, the saving here comes from the fact that this one pointer to Thailand contains more information. It contains the continent information and the capital information. So we've sort of stored all of the country information in one place, and then we're just sort of pointing to those rows of country information via a single value rather than replicating them over and over. Okay, so let's do some of this on in SQLite. We're going to use a sample database called World, which was originally created for MySQL. Now, I've simplified it a little bit, and I've used a slightly more up-to-date version called world_x, but that doesn't matter. The key thing here is that I'll supply you this database, and when you get the database, it will contain 3 tables: city, country, and country language. Now, SQLite is not case sensitive, so instead of city, you could write city, or you could do anything silly as you like, C, capital I, lowercase t, capital Y, and they would all be viewed as the same thing. I've kept the names of the tables all lowercase because that's how MySQL originally produced the database. Normally, by convention, just to make sort of reading things a bit easier, I normally prefer to have table names having a single capital letter at the beginning. And then that just sort of makes it visually easier for you to read along, because you can sort of tell what type of thing something is by whether it's capital letters or lowercase letters or a mixture. Okay, let's have a look at the city table. Now, .schema city. Now, this looks very complicated, and I don't want you to think of it as complicated. We will eventually understand all of this construction, but let's just see the basic parts to start with. Okay, so let me get a marker. Okay, so we have some fields, some columns, some attributes, whatever you like to call them, and these attributes are as follows. Id integer. So that says that the name of the attribute is ID in capital letters, and the type of the attribute is an integer. So it's going to be storing a number. Then name, which is 35 characters. Well, up to 35 characters long. So Bangkok uses B-A-N-G-K-O-K, that's 7 characters. But there are many cities with longer names. Country code, which is 3 characters long. And pop, which is an integer, and that's going to be the population of that city. Now, let me just, the backticks, when you do when I do /id /, that's just a way of permitting attribute names to contain spaces and silly things like that. So it's just quoting the actual name of the column. The name of the column is actually id. It's just that when you specify it in the create table thing, if you want to be absolutely safe, then you do /id. And that's the reason, because if I decide to call a field first name with a space, well, then I'd better put quotes around it so that it knows that that space is part of the same word, if you like, as the name. Okay, so all we need to know now is that we have an ID, a name, a country code, and a population for each city. Let me just look at what these things look like. So this is like exploring the database, so I get some feeling for how things work. I've turned the headers on. I've turned the headers on because I want to see what column corresponds to what thing. We see the headers gives us the four names of the columns: id, name, country code, and population. And we can see here that number 6. So city number 6 is Rotterdam. Its country code is NLD, which stands for the Netherlands, and it's 593,321 people. Again, this data is extremely old, maybe in 1980, it looked like that. Okay, what about country? So, well, the schema for country is, well, each country has a code. Okay, so that's going to be 3 characters long. The code is going to be the NLD part for the Netherlands, for example. So each country in the world has a unique country code that was decided by some international body, and that tells us, so that allows us to uniquely identify a country by a particular 3-character string. Like here, AFG is Afghanistan. Okay, so we've got the code AFG, the name Afghanistan, the capital is 1. Okay, well, 1, what is 1? Well, it's not telling us the name of the capital, it's telling us a reference to the city table. So 1 is a foreign key. Then the continent, which is just a string of text. So just some sequence of characters like Asia, North America, and so on. And then something fancy here that we will talk about next time. Ignore all of the things that say not, null, default, blah. They're all additional things that make those fields behave for themselves when certain situations occur. And finally, the country language. We don't really need the country language for today's lecture, but I just want to illustrate illustrate how it works. So we have a country code. So that's the 3-letter codes that we've mentioned before. I'll keep the code. Then a language. The language is like Dutch, English, Spanish, and so on, is official. We'll look at this in detail later. At the moment, is official is either T, if that's an official language of that country, or F, if it's not an official language of that country. So, and then percentage is what percentage of the country's inhabitants speak that language. So, let's have a look. ABW is some, I guess, some former Dutch colony. The official language is Dutch. So Dutch is a language. T means true, so that's an official language, but only 5% of the population speak that. What the population actually speaks is Papiamento, and 76% of the population speak that. Okay, so as you can see, a country can have many languages. A country can have many official languages. A country can have official languages that aren't spoken by many people, or official languages that are spoken by many people, and so on. One thing you should notice here, though, is that we're using one row for each combination of a country and a language. Okay, so the country language information has been separated out from the country information. We'll come back to why that is in a bit. Okay, so now let's look at connecting the tables. So when we want to find some information that uses both city and country information, we need to somehow combine the information. The way this is going to be combined is by using the code for the country. So every country has a 3-letter code, and the code is enough to uniquely identify the country. Okay, any attribute is called a key if there can only be one row with a particular value of that attribute. So there can't be another country with AUS as its country code, because then we'd get mixed up. We wouldn't be able to distinguish between the Australia AUS and the other AUS. I mean, what would the other AUS be? Probably be Austria. I mean, that would seem fair. Austria. But that's going to cause a problem, because we can't have one country code identifying 2 separate countries. And so Austria has a different country code. It has AUT as its country code. So the code field is then a key of the country table. In the country table, there can only be one row with each particular value of the code attribute. Okay, the schema for country actually told us that this was going to happen. So it said that code was going to be a primary key. Okay, so that's part of the sort of defensive nature of database programming. When the table when the table country was created, the database designer said, I want to insist that all of the values of the code field are different, are distinct from each other. And I will do this by declaring that code is a primary key. We'll explain later what primary means in this context, but for the time being, it's a key. Right. If somebody accidentally tries to enter another country into the table and gets the code wrong, either because they're lazy or because they did a cut and paste or something like that. So here someone's tried to enter AFG's Afghanistan, should be Afghanistan, but they put the name of the country to be Angola, which is obviously incorrect. And so the database says unique constraint failed, country.code, error. And that means it won't insert that data into the database. So the database guarantees that every entry of the code column is different from every other entry. So this is one way in which the database designer, based on their knowledge about the domain, like countries, can specify constraints that will constrain the usage of this database right throughout its useful life. So no matter where and when this database is used, it will always keep enforcing the constraint that we cannot have two different countries with the same code. Okay, so this is all about okay, I'm just going to finish then with a very brief digression on keys. And another way to view a key is that if you know the value of a key, then you can find exactly one row in that table. So a university has a database with many, many students, but student number is going to be a key. We can't have two different students with the same student number. We can't have two different bank accounts with the same account number. We can't have two people with different, can't have two entities with the same tax file number in the Australian Tax Office's database. Okay, so these sort of things are, well, largely what are known as artificial keys. We've just specifically, in order to tell students apart, we've just declared that we will give every student a student number, and there will be just one student with each, and for each student number, there will be one student. Here are some other things that which are attributes, but they're not keys. Like name, there can easily be two students called John Smith, for example. Address, there can easily be two students with the same address. Date of birth, there can obviously be many, many students with the same date of birth. So those attributes are not keys. Now, I just want to emphasize that whether something is a key or not is not dependent on what data the table currently contains. It's a design issue. It's sort of, is this a rule about the business that the database is for that says that never can you have two students with the same student number? Okay, so that's a business rule. If you just happen to have a whole bunch of students with separate student numbers or separate names or whatever, then that's sort of accidentally the name or date of birth identifies a student, but it's not actually a permanent design decision. Okay, so we've looked at how to sort of split a table into more than one table, but next we're going to have to join them back together again in order to get useful information about them.